PLC learnings. In this video, we will see about serial peripheral interface. The SPI bus. The serial peripheral interface bus was developed by the Motorola to provide full duplex synchronous serial communication between the master and slave. Previously, we have seen about the I2C communication. I2C is a half duplex synchronous serial communication, but SPI is a full duplex communication. Full duplex means the sender and the receiver can able to transmit the messages from one to other at the same time. In case of I2C, it cannot be done because it has only one data line. But serial peripheral interface has two data lines so that it is a full duplex. SPI basics. A communication protocol using 4 wires, SPI is a fully synchronous serial protocol. For every clock cycle, one bit is transferred. This is the basic things of the serial peripheral interface. Capabilities of SPI. SPI is always full duplex. Even if the configuration change, that is the mode change, SPI will be full duplex always. Multiple Mbps transmission. And then transfer data bit is 4 to 16. Also, like I2C, you can add more slaves. So, this one is more speed. The speed will be in terms of Mbps. This is one of the big advantage for SPI when we compare it to the I2C. Physical layer of SPI. SPI consists of 4 wires. One is MOSI, master out slave in, and then clock, MISO, that is master in slave out, and then chip select. You will see how these 4 pins will help the SPI to communicate from master to slave or slave to master. At the simplest level, SPI communication consists of a single bus master controlled, that is master connected to a single bus to slave. What it is telling is a master to slave. That is the simplest SPI layer, physical layer. One device acts as a master and the other device acts as a slave. Here, 2 data transfer lines are there, that is MOSI and then MISO. These 2 lines only used to transfer the data. In case of a multiple slaves, master must provide a dedicated chip select CS line for each slaves, and this configuration is like the configuration depicted on the left. Here it is showing SS slave select is equal to the chip select. This configuration is often used in data acquisition system where multiple analog to digital and digital to analog converters. SPI can be used in these applications. So, one disadvantage with the SPI is when the number of slaves increases, the chip select pin, that is slave select pin, also will increase. This will increase the circuitry also. Both the SPI master and slave have the shift registers as shown in this figure. This is the master and this is slave, and this is the shift register. Here only the data to be sent or data to be received will be available. When the master wants to send the data to the slave, first it loads the data into the shift register. The master then selects the destination. This is done by selecting the slave select line associated with the slaves. Here we can see first it is adjusted, then the loading operation will be taken care. The serial clock line is then enabled, and one bit of the data is shifted on the MOSI line with each clock pulse. Here we can see the serial clock is enabled after adjusting the slave select, and then the clock will be given one by one, and for each clock pulse the MOSI line will be adjusted. Since the SPI protocol uses the full duplex synchronous serial data transfer method, it could transfer the data at the same time receiving the slave data using its internal shift register. From the SPI master and slave interconnection diagram on the right side, that is this diagram, you can see that the SPI peripheral uses the shift register to transfer and the receive. Here you can see one side the data transfer is happening, and then the other side data receiving is happening. For example, the master wants to transfer 10001101 to the slave, and at the same time the slave device also wants to transfer the 00110010 data to the master, that is the full duplex time, by activating the chip select CS pin on the slave device. Activating the CS pin means activating, that is pulling it low. Now the slave is ready to receive the data. Prior to the data exchange, the master and slave load their internal shift registers with the memory data. Upon a clock signal, the master clocks out its shift register MSB first via MOSI, that is master out slave in line. At the same time, the slave reads the first bit from the master at MOSI, stores this received data into the memory, and clocks out its MSB via MISO. Continuously using the same principle for each bit, the complete data transfer between master and slave will be done in 8 clock cycles. Here you can see the all 8-bit data transfer. Clock polarity, that is C pole, and clock phase, that is CPHA, are the main parameters that defines the clock format to be used by the SPI bus. First we will see about the clock polarity. Polarity is used to determine the idle state of the clock. That is, here idle or first state is 0, so the polarity is 0. Here the idle state is 1 and the polarity is 1. Here we can see it is low and then it is high. Clock phase. Phase determines at which age the data read-write occurs. In clock polarity, that is 0, and the data read-write occurs at the rising edge, then the clock phase is 1. If the clock polarity is 0 and then read-write occurring at falling edge means the clock phase is 0. The clock polarity is 1 and the read-write occurs at falling edge, then the clock phase will be 1 and then polarity 1, here the rising edge, then it is 0 clock phase. We can see the same here. Here it is the clock and then the sample. Rising edge and then this is the falling edge. Modes in SPI. The frame of the data exchange is described by two parameters, as I said earlier, that is clock polarity and the clock phase. This diagram shows the four possible states for these parameters and the corresponding mode in SPI. That is mode 0, mode 1 and mode 2, mode 3. When clock polarity and phase both are 0, then it is mode 0. Like that it goes on. First we will see mode 0. The data must be available before the first clock signal rising. The clock ideal state is 0. The data on MISO and MOSI lines must be stable while the clock is high and can be changed when the clock is low. The data is captured on the clock's low to high transition and propagated on high to low clock transition, as shown in this diagram. When the chip select pin goes low and then the clock varies, that is in rising edge. Next we will see the mode 2. The first clock signal rising can be used to prepare the data. The clock ideal state is 0. The data on MISO and MOSI lines must be stable while the clock is low and can be changed when the clock is high. The data is captured on the clock's high to low transition and propagated on low to high clocks. Mode 2 is somewhat similar to the mode 0. The data must be available before the first clock signal falling. The clock ideal state is 1. The data on the MISO and MOSI lines must be stable while the clock is low and can be changed when the clock is high. The data is captured on the clock's high to low transition and propagated on low to high clock transition, as shown in this diagram. Mode 3 is somewhat similar to mode 1. The first clock signal falling can be used to prepare the data. The clock ideal state is 1. The data on MISO and MOSI lines must be stable while the clock is high and can be changed when the clock is low. The data is captured on clock's low to high transition and propagated on high to low clock transition. How to select the mode in SPI? You can select the mode by configuring a bit in a configuring register. Your device manual will tell you which bit it is. As for how to configure clock phase and polarity, it depends on the device you are working with. Typically, the device has a register with bits corresponding to clock phase and polarity. This bit can be manipulated to bring the device in the desired mode. Let's see the advantages and disadvantages of SPI. SPI is full duplex communication with high speed. This higher throughput than I2C protocol. No limit to 8-bit word in case of bit transferring. Arbitrary choice of message size, contents and purpose. Simple hardware interfacing. Typically low power requirement when we compare to I2C. And disadvantages. Require more pins on IC package than I2C. It needs 4 pins. no hardware control, and then no acknowledgement signal. We can't get the act from the slave. Thanks for watching. Don't forget to subscribe to this channel. Post your doubts in the comments. Thank you.